I just keep hitting this button, I will sequence to the sides. I will. Okay. So thank you, VJ, for inviting me. This was a particularly tough talk to prepare, and I kept chewing on it and chewing on it and chewing on it, and finally, this morning I prepared it. Because I couldn't get it right. It's not clear that I've gotten it right either. Part of the problem is I don't know anything about parallelism, and the workshop is about parallelism. But the title is intriguing, Integrating Parallelism into the Undergraduate Curriculum, and I know quite a bit about the undergraduate curriculum. And VJ was good enough to provide me with a number of questions that could be legitimately dealt with. And so the more I thought about this, the more I thought that we've got a big problem with the undergraduate curriculum, and maybe parallelism is going to provide the vehicle that we can address the problems of the undergraduate curriculum within the context of promoting parallelism. You see, the title of the workshop is Integrating Parallelism Throughout the Undergraduate Curriculum, but it's part of the larger vehicle of pathways to revitalize undergraduate computing education. So how do we blend those two into a talk? And that's what I've been struggling with since I said yes when you asked me several months ago. It's amazing, several months, and yet it's this morning that the thing actually gets done. When am I going to learn? So my title is teacher. You notice I prefer that title, even though the university prefers one that's a little bit more grandiose. Because teaching is the thing that I enjoy most about being a college professor. And I do have my 10 Commandments of Good Teaching, but this is not the right forum for it. So I'm just going to flash that up there for a moment and tell you that if you give a damn about good teaching, that I might encourage you to look at my website and see whether you, who knows, maybe I have something to say, or you can delete and move on. So, back to the what I want to do today. What can we do to revitalize undergraduate computer education?
Yep. Those three little words, I don't know.
Exactly.
Okay.
Yeah. What else would they be? A professor who is not able to say, I don't know. Yeah. In fact, the real problem is that if you BS, kids ask a question you don't know, and so hell, you're the professor, you got lots of experience, so you come up with an answer. And so this is a pragmatic reason. There's an idealistic reason also, which is that the university is, you know, the one place where you ought to be interested in truth and knowledge and, you know, getting it right. You can't have that at the university. Where can you have it? But a pragmatic approach would be that if a student asks a question, you BS, and somebody knows the answer, you've lost all credibility. You may as well just not conduct the class ever again. Yeah. So I don't know is critical. And the further along you get in this business, the more you realize that there's far more that you don't know that you do know. And that's okay. That's absolutely. Anyway, so what can we do to revitalize undergraduate education? The answer to everything today is embrace parallelism. Why? Because now we have multi-core chips, right? Intel and AMD, etc. Even IBM has a multi-core chip, or 2, or 3. And so we start out with Core Duo. And by the way, the reason why we have multi-core chips is these guys at Intel and IBM, anybody from AMD here? They may not be willing to let you know this, but the real reason for multi-core is that there's so many transistors on the chip that to utilize them to do something serious, like a better branch predictor or a trace cache that works or something else, is just too hard. And if they just use those transistors to make the L2 cache bigger, you end up with a core and an L2 cache. Much easier to just step the reticle and have Core Duo, now quad core, and octo core. We've got a number of chips that have octo core now. In fact, cell processor, actually cell processor had 9 cores. Larrabee, the Intel chip, which everybody's going gaga over, Starts off with 32 cores, and who knows where that's going to end up. There was a panel at IPDPS this year. What are you going to do with 1,000 cores, see? And the nonsense has really gotten out of hand. So this talk that I was asked to give at the supercomputing conference in Germany in June, this Hans Mohrer's conference, the guy who wrote up the blurb to introduce a couple of talks said, what do we do with 1,000,000 cores? See, once you get to 1,000, which you really can't deal with anyway, what the hell, 1,000,000? Now, that's really silly, 1,000,000 cores, you know? Well, we're going to have 50 billion transistors on chip, and so 50 billion transistors, you could have 1,000,000 cores. When I was about 4 years old, my father taught me how to do division. So 50 billion divided by 1,000,000 is 50,000, which means the number of transistors on the chip, assuming that there's no interconnect between these cores, just the cores themselves, you know, which is also silly. There's so much nonsense out there in this multi-core. But it provides this vehicle. I guess the individual core for this 1,000,000 core chip would be 50,000 cores. So we're going to have a chip 5 years from now with 50 billion transistors on it, but the individual microprocessor will be vintage 8086, or something that's 35 years ago. So the silliness continues. As I say, the Bobo comments continue. So instead of asking, how do we integrate parallelism, what I'd rather do today is ask, is there anything in the undergraduate curriculum that needs fixing? Is there any evidence that something needs fixing? So many companies don't want to hire our graduates. They say that the graduates are coming out with degrees that the graduates really don't get it. Maybe we're not teaching stuff that prepares the graduate for taking his or her role. Secondly, we're no longer getting the best students. It was once a time that the best high school students going into the freshman year would elect either electrical engineering or computer science. And that's not happening anymore. Now it's like the third or fourth choice among the best high school freshmen. I'm not suggesting we can't fill our classrooms, we can, but filling our classrooms with yo-yos is not my idea of what we want to be doing. And so the question is why? And the cop-out answer, which people give, it's the easy answer, you know. You don't have to even deal with the problem. You can just say, well, you know, we're outsourcing jobs, and so offshore, and so there's no attraction to a CS degree. So maybe we need to look deeper. What are we doing wrong? And importantly, can parallelism provide an opportunity? So the call for participation provided topics. Parallelism within the curriculum. Is there parallelism within the curriculum? And so I don't know how many of you are hardware people, but hardware has always had parallelism. You know, there's this architecture guru. Too many architecture gurus don't really get it. But he made the pronouncement that hardware is sequential. Hardware is not sequential. In fact, any hardware description language worth its salt says you have to explicitly say when you want to do something sequential. Hardware is the place where everything is working all the time. You know, this electron doesn't say, you electron, you go first, and the other electron, oh no, you're an older electron, so you go before me, and it doesn't work that way. All the electrons are busy all the time. Hardware is inherently, innately parallelism. So this business that, you know, there is no parallelism, or to think about, you know, so one of my bullets, which I don't have here today, thinking in parallel is hard, and then I get rid of the in parallel. It says thinking is hard, you know. So the hardware has always had parallelism. What about the software? Until we start with freshmen. I teach the freshman course. I also teach my advanced graduate course in microarchitecture for students who then want to go on and design chips. You know, Mike Chevenow, lead designer at NVIDIA, took my advanced graduate course. Sprangel, who's in charge of the architectural Larrabee chip, took my graduate microarchitecture course. But I also teach freshmen. And I decided last time, every other fall I teach it. The last time I taught it, I said, let me try an experiment with respect to parallelism. The last lecture, actually the lecture before the last lecture is free-for-all. They can ask me anything they want. But the lecture before that, I decided to try some things out. And I said, supposing I want to compute factorial, let's say 10 factorial. And these are freshmen at the University of Texas, so they know what factorial is. And I say, supposing the only thing that matters as far as execution time is multiplies. And how many multiplies are going to take? And so being bright and having learned how to multiply, they do 10 times 9, times 8, times 7, times 6, times 5, times 4, times 3, times 2. You don't bother multiplying by 1 because that doesn't have a big effect on the answer. 8 multiplies. And so it takes 8 units of time. And I said, yeah. Now supposing you had more than one process that could deal with the problem at the same time. Now, how many multiply units of time does it take? And I gave them about 2 or 3 minutes to think. And half the class was able to get it. Say, okay, I would direct this processor to do 5 factorial, and then I would do 9 times 8 times 7 times 6, 9 times 10 times 9 times 8 times 7 times 6. 4 multiplies. By the time I get through with that, 5 factorial has been computed here. Multiply it by this. I've reduced it from 8 multiplies to 5 multiplies. So these are freshmen who've never been taught about parallel programming before, just thrown out the question. Supposing you had 2 processors and are able to get it. The point being the obvious one, if we stop telling people that it's hard and just make them aware, is there something that could prevail? So another bullet that's called for participation said parallel, so I'd use parallel star in the computer science sense of the word star. And there were several separate bullets, debugging tools and parallel projects and parallel demonstrations, et cetera, and I am not going to deal with that at all. But they did give me a couple of bullets that I can deal with. Computing curriculum reform. What should we do about, is there something that needs to be done there? And the answer is absolutely. And the most critical thing is what course comes first. In fact, I'm delighted that the people at Purdue are putting a lot of energy into what to do in the freshman year. Because what comes first is critical, because everything then builds on what comes first. And it's not enough to just say, well, it doesn't matter where it comes, you know. When they graduate, they'll have it all.
With Yale, that's parallel. You just launched a sequential thinking on the curriculum. I'm just in heckling mode.
So that's okay. You may actually have 2 things come first concurrently, and then it would be parallel again. But it may be that you want the first course to be that foundation from which we then go in parallel. Right. In fact, as you'll see, I do have a slide or 2 on my motivated bottom-up approach. And one of the big things about that motivated bottom-up approach is that it comes first, then the first serious programming course can build on it, and the first serious hardware course can also build on it. And the curriculum on why objects are bad and why Java is particularly bad. And then the call for participation gave me a number of related topics which I just couldn't resist. Any other related topics? Yeah, PowerPoint is harmful. So I'm using PowerPoint here. The reason I'm using PowerPoint here is that I'm not so much teaching you as I'm giving a presentation. To do this presentation with a blackboard, which I would prefer, would take so many hours that it just, I wouldn't be able to keep you sitting in this chair that long. Classroom teaching is very different from making a presentation. In fact, I get disgusted with these letters that universities ask me, we're looking at hiring this guy. Can you tell us about his research? Can you tell us about his teaching, you know? And I say, I never took a course from him. How can I tell you about his teaching? Say, well, haven't you heard him make presentations at conferences? I say, yeah, but what does that got to do with teaching? Okay? What you do in that environment of a conference and what you do in a classroom are very, very different things, and they require very, very different skills. So, yes, I'm using PowerPoint, but I'm not teaching a class today. And in fact, the good students will tell you that the lecture would be improved enormously if the professor would leave his laptop at home. Abstraction is grossly misunderstood. And in fact, I'm going to hit on that a couple of times. People, for some reason, think that abstraction is beautiful. You know, it's a productivity enhancer. You know, here you are in Raleigh, North Carolina, and you don't know how to get to the airport, so you get in the taxi and you say, airport, airport. 2 syllables. Now, you could say to the cabbie, if you did know how to get from here to the airport, put the key in the ignition, turn it on. Now ease up on the clutch. Now turn the wheel this way. Now go to the end of the block, make a left turn. That productivity is not enhanced. If you just say airport, you can sit back, read your newspaper, and eventually you get to the airport. And when you, on the way to the airport, you say, wow, the Kitty Hawk Memorial, you know? Well, the Outer Banks is not on the way from here to the Raleigh-Durham Airport, you know? That's kind of out of the way. But if you don't know the way to the airport, you could, in fact, find yourself going by way of the Kitty Hawk Memorial. In fact, I once had that experience where I asked a cabbie, picked up a cab in the financial district of New York, and I said, this is the shortest way to the airport? It says, Midtown Tunnel is not, 59th Street Bridge is not, we're going over the Triborough Bridge? He said, oh yeah, I know what I'm doing, you know, and so he took me to the airport. And the fare was ridiculous and I almost missed my flight. Abstraction is great as a productivity enhancer, provided everything below works out. So we want to talk about that a little bit. And in fact, my way of teaching is first you do an example, then you abstract. In fact, that was one of the things that, so I like Dijkstra a lot. That was one of the things I didn't like. Dijkstra and I used to go like this with respect to this concept. He felt that anytime you come up with an example, you're not really capturing the essence and the beauty of the abstraction. I said, yeah, but people learn better if they can see an example first and then they go to the abstraction. And students can handle serious material, and our curriculums don't need to be dumbed down. Sugarcoating is unnecessary. So the call for participation gave me these things to kind of, but better than that, oh, I forgot that. Forget this year's fads. Yeah. So new fad comes out, we jump on it. Java, for example. By the time they graduate, Java's not going to be the language that they use. Probably be C#. So 5 years from now, we'll be teaching C#. But by the time they graduate, it won't be C#, it'll probably be D flat. See, so that there's no way that jumping on these faddish bandwagons is providing stuff that's useful for them 40 years down the road. I suggest we teach the fundamentals. Which seems people getting away from that. Why do we need math? Why do we need physics, you know? We need web design. Then VJ gave me a number of questions to chew on, which was terrific. Says, what should we teach? The fundamentals, more math. If I had a year to just stop and just take classes, study, I think I'd probably study statistics. It's pervasive across everything that we do as computing people. And yeah, you know, I had the graduate course in statistics when I was a graduate student from Parson, actually, which was a great course. But wasn't enough. I should know more. What should we not teach? Right? The color. I don't use color a lot. You know, you'll notice that my PowerPoint resembles transparencies. In fact, Sanjay says, you know, you're incredible, Yale, Patt. You've taken this fantastic technology called PowerPoint, reduced it to the overhead transparencies of 50 years ago. But the color is, but I now learned to use color. So I've improved in two regards. One is I can now use color in my PowerPoint. The other is I can single step through the slide. In the old transparency days, I used to have to put Post-its. See that I don't know whether you've seen. Have you seen my talks with my Post-its? Yeah. So, but you don't go back. You don't go back years ago. So before Post-its came around, what I would do is turn off the overhead and put pencils down. See, then turn back the overhead, and then I would lift the pencils off. But this is, I just push the button. This new technology,
It's abstraction.
So I got another 50 years or so of teaching before I retire, and I'm looking forward to, what this technology is going to provide. So, what should we not teach? 5 languages, web design, Excel, the latest fad. Should we teach concepts or are tools important? Another one of your bullets. So I have to say, which tools? So, with respect to tools, so I don't teach tools, see? I assign tools. I said, oh, you don't, in fact, in my computer design course, they're going to use Verilog. Okay, you don't know Verilog? Here's a manual. And by the way, that's one of the pluses. So how many computer science people are there as opposed to computer engineers? Who's computer science? Yeah, a lot of you. So I'm going to pick on you for a second. One of the things I've noticed, the difference between computer science students and
You have to ask the other question.
Huh?
Who's computer engineer?
Okay, who's computer engineers or electrical engineers? Yeah. Okay, good. So it's about half and half maybe. Yeah. So when I was at Michigan and I taught this undergraduate course where they didn't design a computer from scratch, but they had to do some coding at a low to make a data path actually work. And so I had a choice whether to use C, which all the computer science students knew, or Verilog, which was the right answer, which all the engineering students knew. And what did I pick? C. Why? Because I knew that if I picked Verilog and didn't waste class time teaching Verilog, all the CS students would complain to the dean, he expects us to know this, and he's not teaching it. Whereas if I use C, all the engineering students would say, I guess I got to learn C. And they take a manual off the shelf and they teach them C, and the first assignment would take them longer, but then they get up to speed. So what's the bottom line? Teach what they can't learn on their own, assign them to learn on their own what they can learn, but, and most tools fall in the second category, and most tools will be irrelevant by the time they graduate. So, yes, they have to use tools, and tools are important. They also need to have to drive, because how do they get from home to the campus? But I don't give them an A in getting from the home to campus. I don't give them an A on the tools. The tools are something I expect them to master as they need. And what problems do I see in CS and computer engineering education? And you can see I'm on a roll. Not enough emphasis on fundamentals. Too much sugarcoating. This one is bad. Too much concern for retaining students who should be encouraged to leave. And so I was in the pizza place. This kid comes up to me and says, Dr. Patt, let me shake your hand. I had you in 306. 306 is the freshman course. And I have 450 students in the class, so I don't get to know everybody personally. And I say, how'd you do in the course? He said, I made a D. And why are you so happy? Because you convinced me that this was not for me. I switched my major to history, and I've been getting A+ ever since. I consider that a win, convincing him to move to history. See? So not every student who signs up. When I was at Michigan, kid comes up to me after the first midterm. He says, I need to know whether I have any chance of passing this course. I made a 2 on the midterm. This is 2 out of 100. So I said, well, you got to tell me more, because a lot of kids will blow off the first exam. They're away from home. The parents aren't telling them to, make your bed and study, do the homework. They've discovered girls, they've discovered alcohol, and they've discovered soap operas or something. And so studying. So in high school, you cram the night before the exam, and you'll do fine. So the kid made it 2. So I had to be sure that he was going through the right motions. So I asked him, you know, you've been working, you doing the programs, are you doing the problem sets, are you in a study group, you know, ... And the answer is he's been doing all of that. He's taken the course seriously, and he earned a 2. I said, doesn't look good. He said, would you mind writing a note to that effect to my father so that I can change my major to music, which is why I came to Michigan in the first place? A lot of these kids are in there not because there's a fire in the belly, but rather because somehow they think that this is the thing, not somehow, the parents think it's the thing that they should be doing. So, too much concern for retention, and I think some students should leave. Too much reliance on memorization. In fact, that's how they got. So at UT, University of Texas, you have to be in the top 10% of your high school class, or you're not going to get in. And how do you get there? Memorizing. And so the reward structure, I don't think it's unique to Texas. I think it's a universal. The reward structure is such that memorization wins. And by the way, the kids memorize for only one reason. And we need to get past that. Also, too much teaching by those who don't get it. At most universities, getting a senior professor to teach the freshman course. In fact, I guess for some reason that may be why I get stroked by the administration. Here's an endowed chair teaching the freshman course, which is unusual. It shouldn't be unusual. The senior faculty, the ones who have the broader picture and the insights, ought to be the ones that are teaching the freshmen. The assistant professor should be teaching the graduate courses, since I don't need to teach a course to acquire graduate students. An assistant professor often does. So senior faculty teach freshmen. Junior faculty teach graduate courses. And non-faculty, that is lecturers or somebody who needs a job or something or other, unless they really know what they're doing, teach nothing. Okay? There's too many lecturers that don't really get it themselves, and once you don't get it, you're useless in a classroom. Yeah, you can put up the pattern on the blackboard that you've memorized or something, and the kid memorizes it, but that's not what learning is, and it makes that memorization thing go worse. My ex-wife got an A in geometry, and she was totally math clueless. And how'd you get an A? Well, you know, the teacher would come in, put the proof on the board, and then we'd memorize the proof. So we'd come in and we'd put the proof back on the paper. We get 100%. In fact, my favorite story, by the way, plain geometry in high school is, in my view, probably the most important single course in the whole high school curriculum. See? Good, I got one fan. Yeah. So my kid's sister, who was not math-phobic, she had me and my younger brother, 2 older brothers to, you know, to work with her. So she loved mathematics and plain geometry in particular. And I'm home for the weekend, and she gives me her exam paper, and I see a big 0 on one of her proofs. And she says, Yale, you know, I've looked at this proof, I don't know how many times, I can't figure out what was wrong, you know? So I looked at the proof, and guess what? There's nothing wrong. See, and then it hit me, see, because, you know, I went to the same high school as my kid's sister did, right? Surprise, surprise. And I knew her math teacher, her geometry teacher. Hell, I knew more geometry when I was in high school than he did back then, you know? And so I knew exactly what happened. He didn't know any geometry. Now with PowerPoint it's different, but in those days, what he did is the night before he would copy the proof from the textbook, didn't understand it, but he could copy it, goes in a class, puts it on the blackboard, the kids are sitting there, they take it down, you know, from the notes of the teacher to the notes of the students without going through the brains of either. And then the night before they would memorize the proof, they'd come in, he'd give them the same thing to prove, 100%. Not my sister, see? My sister never crammed anything. The night before a geometry test, she might spend 5-10 minutes reviewing some stuff, but then she'd go into the exam, hit it to me, baby, you know? And then she'd look at what she has to prove, and she'd figure it out, and she'd lay out the proof. He didn't know enough geometry to be able to follow her proof. And it was not the proof in the book, so therefore it must have been wrong, and he gave her a 0. Yeah, the story has a nice ending, because what I did, I just wrote a note in the margin. Dear Mr. We'll keep him anonymous, I guess. Who knows what's going to happen with this videotape. So, dear Mr. Such and Such, this proof is exactly correct and deserves full credit. And he gave her full credit. I don't know whether he gave her full credit because he knew I wouldn't go for points for my kid's sister, or whether he was afraid I'd turn him in. I don't know, but it has a happy ending. And I think it's serious. I think people who don't get it in the classroom, they can't provide the insights. You can't be 3 pages ahead of the class. That's bad education. And while I'm at it again, get rid of PowerPoint. Oh, multiple guests. So I was at so Microsoft has this faculty summit every summer. They didn't invite me back last year, so maybe I said the wrong thing the year before. They had this education group, and they want to come up with a common set of test problems so that a professor can use this set of test problems from the common set, right? And what are the test problems? Multiple choice, excuse me. Multiple choice. If you're giving multiple choice questions, are you really testing what the kid knows? In fact, in my freshman course of 450 students, I don't give multiple choice. I give thinking problems. A good test problem is one where the kid thinks for 20 minutes and then writes for 1 minute. Right? That's what I used to tell whether the kid gets it or not. You say, my God, how long does it take you to grade the problems? Well, so what you got to do is up front put a lot of energy into coming up with problems that require the kid to think, but when you look at what's on the sheet of paper, you can grade it quickly. And that doesn't come easy, and so I spend a lot of hours with my TAs making up the exam. But the grading, because we can get it done, 450 students, and we grade it as a team, and we can get it knocked out in 1 day. So, VJ also said, what innovations in research will fundamentally change what we teach? I hope I'm not ruining the rest of the afternoon with this, by the way.
No, absolutely, go for it.
Okay. So the operative word here is fundamental, see? And so the answer is nothing, see? Probably none. Things are moving much too fast, and we need to emphasize the fundamentals. Now, that's not to say that we don't take what we can and move it into the curriculum to enhance. But that's very different from the sense of the question that I got was, what innovations will fundamentally change what we teach? A lot of people, this latest thing, will just stick it into the course. Doesn't belong in the course, doesn't enhance the course, but somehow they teach around that latest thing, and you end up with not really providing what the student's going to need to be good for the next 40 years. What computing research should we do to make our educational endeavors more successful? So I got a better idea. Spend quality time in the classroom. Pay attention to what you're teaching. Think about what went on at the lecture to see, what are you doing right, what are you doing wrong. Talk to students, talk to your TAs. My TAs have to attend all my lectures. Why? Well, for one thing, supposing I screw up the lecture. Only a damn fool thinks every lecture is perfect. If the TA isn't sitting on my lecture, how does he or she know when the kid asks a question whether it's the kid's fault or my fault? They sit in the lecture, in fact, this happens, and I can almost read it on their faces. Oh my God, is he blowing this one? Am I going to have my hands full explaining what he's just butchered, see? So I require my TAs to attend my lecture. The first thing I do after each lecture is say, okay, how did it go? I don't want to be patted on the head. I don't want to be complimented. I want, real constructive criticism. What worked, what didn't work, what did I assume, what did I go over too quickly, etc. So what I would argue is to make our educational endeavors more successful, then invest more time in your teaching experience. And if you wish, so in some sense, maybe I'm advocating you're doing research in education. Not too much in research and education I have a problem with, but I think that most of us could be, yeah, you got a question?
So it seems like other disciplines are better about capturing and sharing best practices than
I'm sorry?
education.
capturing and sharing best practices than education is. So many professors just learn it on their own.
Yeah,
Learn how to teach. on
Yeah.
their own.
yeah, that's true.
And what I hear you saying here is maybe that's a structural failing, that there needs to be more effort in sharing and.
So I wasn't saying sharing, although it's certainly true that I do get into dialogues with usually my junior colleagues. My senior colleagues don't want to listen to me because, you know, I'm beating up on them. But my junior colleagues tend to be more interested in what I have to say about the teaching experience. So maybe that's true. Need to deal with that. Okay. Maybe the panel can deal with it, or we can talk about it later on. What role do teaching schools, community colleges, and K-12 have? Thank you for that one. All can help. Teach thinking and understanding and minimize memorization. By the way, we have a serious problem in K-12. That's why one of the reasons I was hoping that your NSF people were here today, because the AP thing isn't working. I mean, it really is broke. Yeah, in fact, we have a very serious K-12 problem. Somehow, you know, what I'd really like to, in fact, maybe it's available and I just don't have it, is what I'd like to have is the slide the way you see it, and then the slide of the whole slide. And that way, see, with the old transparencies thing, I could be looking at my last slide while I was covering this slide.
That's available, yeah.
That's available. Okay, so Sid, you're going to have to do that for me, because I really, because you see what I just did. You know, I got through saying something and I had thought about it and put it on the slide. Now the next thing, and it's in red, and you see that, you know, I don't use color. I only use color once in a while.
I agree. So the AP course does not work. You're absolutely right.
And
why doesn't it work?
Huh?
Why doesn't it work?
Well, patience.
Okay.
This is AP Computer Science course or AP in general?
AP and computer science.
This is the AP Computer Science
Yeah.
course and exam.
So, second bullet, good students are turned off, and decreasing enrollments in the colleges from the good. We're not getting the best students anymore, and I think the AP course, so the AP course is a Java course. So it's another thing I get to do. I have 450 freshmen in my class. I talk to some of them after class. In fact, they come up and they want to talk to me. You know, end of the lecture, and I'm going to go back to my office, but it usually takes me 20 minutes before I can leave the room, because they have questions and they want to talk. And they love my course, which we'll get to in a moment, because they're getting it, they're understanding it. And what they're getting in the AP course is Java. Pattern, don't bother me with understanding what the pattern is. Just memorize the pattern. When I get the problem, I try to fit the problem to the pattern. I've understood nothing. So the good student wants to know what's underneath the hood. The good student wants to understand why the things work. And Java, by the way, is particularly bad. I didn't ever realize this. Jim Goodman, now he's teaching at University in New Zealand. And he said, so when my book first came out, he said, bad book, because I'm going bottom up. He says, the way you want to go is top down. Computer scientists think top down. I said, no. When you think top down, you're memorizing all the time. You want to think bottom up, since you're building on what you already understand. So that's because you're an engineer. Then I see him a couple of years ago. He's been in New Zealand for a few years. He says, Yale, you're absolutely right. He says, I'm teaching Java. Java, by the way, is worse than C. C would be sort of okay, because in C, you get a compile time error message, and if you really get it, which is not trivial, and you really fix it, then the program will run. Now, the problem is, of course, that most of these kids, fixing it means getting rid of the compile time error message, guaranteeing the program will never run. But in Java, you can, by trial, so the problem with the kids who don't get it is they throw things at the program until finally the thing is just a disaster. In C, in Java, it's not a disaster. In Java, by trial and error, they finally get it to run. So so this is Jim Goodman talking now. They complete the course with an A while remaining clueless about the material. So Java's particularly particularly bad. The good students are being turned off by the Java course in high school, and they elect something else in college. Yeah?
You say you work by Java allows you to do this. Doesn't Java have
I'm sorry?
Doesn't Java has stronger typing?
So I'm not a Java programmer, so I don't want to get into detail. That's all I'm telling you is people who have taught Java tell me that by trial and error you can actually get the program to run while remaining clueless. If you don't agree with that, huh?
That's true in any language.
That's not true in C.
Yes,
Yes,
it
it
is.
is.
I mean, this is the 1,000 years of it.
I'm sorry?
This is 1,000 monkeys typing for 1,000 years, producing all the work.
So I don't believe that for C. I think, so my experience with C is if the kid doesn't understand and he tries things, he doesn't end up getting it to work, he ends up with a mess on his hands. You find it different, then that's your experience. My experience is that the kid makes a mess and finally takes it to the TA, and the TA would, blech. And so the TA does the first half of the program for him, and says, now you finish it. And so what does the kid then do? Goes to the other TA. So some anecdotal observations. The Viewpoint article, for those that are interested, I recommend you read it. Communications, the ACM in July. And the title, so Viewpoint is somebody makes a point, somebody makes a counterpoint. And the point made by Robert Dewar and the counterpoint made by Owen Astrahan. And the title was CS Education in the U.S. Heading in the Wrong Direction. So I'm going to talk about that more momentarily. Email from a new education director. There is a corporation out here in the U.S. that puts a lot of energy into interacting with universities. And I just got email recently from their new education director explaining the bottom-up approach as opposed to starting in Java. And the email back was, after 30 years of teaching, I know. Arrogance. So I did not respond after 45 years of teaching. I still don't know, which is what I probably should have done. And the thing was, arguments about what comes first are unimportant. Because at the end of the day, you know, they get it all. And I think what comes first is critically important. And then I've already mentioned my freshman course. Intro to Computing, it's required of all majors. I get about 450 students each time. And what's good is I get these kids, they're out of high school. The first 6 months, the first half of the semester course, I have to break them of the fact they're no longer in high school and that memorizing is not going to make it in my class. Many of them have taken the AP course, and almost universally, unanimously, they love what we do because they're getting it. And they say, now I understand, whereas before, no, they were clueless while doing well. The freshman course has no prerequisites, so you can come into the class never having seen a computer before. In fact, the first discussion section is my TA showing them how to log on and how to send email and how to surf the web. Now, you might think that everybody knows that, but that's because you're on one side of this digital divide. There are plenty of kids that have never, used a computer before. And so, how do they do in the course? They're in the same course with these hotshots. And as a group, they don't do as well, but there are plenty of students that are in this group that get A, and there are plenty of students that were the hotshots in high school that don't get A. My feeling is the reason they don't get A is they don't take the course seriously until it's too late and they're in trouble. The Viewpoint article, Roger Dewar's point was that we have a serious problem with critical software. And Owen Astrahan's counterpoint, this is my opinion of this, by the way. I invite you to read the article and then make up your own mind. Owen Astrahan's counterpoints, I felt, were in many places misguided, but was really trying to encourage an all-inclusive kind of group. So Dewar said CS curriculum being dumbed down, partly for this enrollment pressure. I know that that's true. In fact, there was one school where there were two departments, ECE and CS, and one of the guys wanted to use my freshman book. which is glitz-free. In fact, the first edition of my book had no color whatsoever. Second edition, now we put in one color, similar to the way I've used one color here. But I'm not into glitz, I'm into hardcore stuff. And the department as a whole said, you know, if we do that course in the freshman year, we're going to be losing all the freshmen to the other department that's doing Java. And you know, you end up with nice programs with lots of color and glitz and everything else. Java, so Duar says, which of course I agree with, Java is bad, it hides too much, far too much magic. I had a former colleague at Michigan, I should have the slide for it here so that you can read it and laugh. His Ravi Shankar, C.D. Ravi Shankar, and the quote from him is, information hiding is all well and good, but shouldn't the student know a little information before he starts to try to hide it? Too much magic, and I'm anti-magic. The CS, another bullet of the war, CS faculty take it for granted that all large systems have bugs. And by the way, Astrahan's counterpoints to these bullets, CS curricula are being dumbed down. Astrahan says, not at all. We chose Java because it is the right language to teach these important concepts. CS faculty take it for granted that all large systems have bugs. He says, well, that's just a fact of life. And he quotes Brooks's mythical man-month as saying that, you know, large systems are just too complicated. How about chips? Hardware designers don't take it for granted that the chip, when it ships, so I got to get this carefully right. They know that it's tough to get out all the bugs, but they work darn hard getting out those bugs. How do I say this? There's a far different mentality, I believe, about the chip designer and the large software system writer, which is to say the software, well, you know, there's going to be bugs. The chip designer says, no, bugs are bad. We got to get the bugs out. It's certainly true that we never get all the bugs out, but some bugs actually never see the light of day because they don't influence anything. Noir points out an example of a senior programmer who couldn't figure out a problem from the high-level compile time messages. So he generated the assembly language core dump and then went over it to find out where the problem is. Which I think we do. When we really understand, when we really have a problem, we can't crack it up here. We take it down to the level we can crack it. And he mentions a CS graduate that was just amazed. Why would you ever want to do assembly language? And Astrahan agrees with that. He says, assembly language. Next thing you'll tell us you want to go back to punch cards. So I think going back to, this is Astrahan's comment, punch cards and assembly language, I think there's a disconnect there. And then he says, fancy visuals do not compensate for deep understanding. Astrahan says that Java is only the first language, not the only language. Back to my point, what comes first really matters. Duar's arguments are based on fear, uncertainty, and doubt. That's and by the way, Astrahan gives it a name. Fear, uncertainty, and doubt. FUD. They're based on FUD. Duar would take us back to, I already said that. And then, this the scary part. He invokes Sisyphus. Remember the myth of Sisyphus, where he's supposed to push the boulder up the mountainside, and then before he reaches the top, it pulls him all the way back down, and he goes for eternity doing that. Astrahan invokes Sisyphus, saying that these people like Duar and Dijkstra that are pushing uphill against, now I wish I had done the whole quote. I left the dots figuring that I would remember the whole quote. Against the, damn it, I should have brought the paper. The enormous number of boulders representing the reality of computer science That is, you're pissing against the tide in some sense. And that's scary, because the tide is now this Java mentality. I think we need to do. The other thing he says is that, which he misses Dewar's point. Dewar's talking about critical software. After he says, you got to understand, in computer science, we have to teach computing for everybody, not just people that are going to write software. We have to do literacy courses. We have to do other stuff. That is, there's an inclusive attitude of, the nice, warm, fuzzy thing. Now, that's true. It's not what Dewar is talking about. It's okay to teach a course, a literacy course. That's okay. But don't confuse the literacy course with the course for serious people. And then he notes that the CS professor's view is influenced by where he came from, Abstraction came from a liberal arts program. I won't accept that. That is, it may be that you're influenced by where you came from, but that shouldn't matter. What should matter is, where are the students you're teaching going to go? So you may come from engineering, you may come from liberal arts, but you're teaching students that may go here, here, and here. That's what you should be focusing on.
I didn't follow that. This one is from a liberal arts background?
I'm sorry?
Oh, yes.
Really?
Yeah.
Actually, you're
That's just typical. One of the things you're supposed to learn in a liberal arts education is critical thinking. That's the first thing you're supposed to get.
So what do I want to do in the first course? Get rid of the magic? Point of variables, the reason why it's magic is because people don't know that in a memory location that